Hello and welcome to another Mr. Mario Maths video. Today we're going to be attempting an OCR MEI question from their Decision 2 paper in June 2016. Specifically we're attempting question 3. Before we get started with this question, I'm going to make it clear that this is an educational video for the intent and purposes of helping students with a simplex algorithm using the new specification EdXL qualification. Which means that any time we use a simplex algorithm, I'll be modelling it how EdXL would like you to model it on the new specification 2019 for the math specification, rather than how OCR MEI would have done it previously. So we've got this question, and Neil is refurbishing a listed building. There's two types of paint that he can use for the inside walls. One costs £1.45 per square metre. The other costs 95p per square metre, and he must paint the lower half of each wall in the more expensive paint. He has 350 square metres of wall to paint and a budget of £400. The more expensive paint is easier to use, and so Neil wants to use as much of it as possible. And we've given an initial linear programming problem to help Neil with his purchasing of paint. X is the amount of expensive paint purchased, and Y is the amount of less expensive paint purchased. And in the question, we're told that Neil must paint the lower half of each wall in the more expensive paint. So if Neil must do that, then the amount of expensive paint must be at least the amount of less expensive paint. So we know that X is going to be greater than or equal to Y, which rearranges to give Y subtract X is smaller than or equal to 0, which is the purpose of this inequality. So we get that independent accuracy mark for giving the reason he must paint the lower half of each wall in more expensive paint. In the question, we're also told that he has 350 square metres of wall to paint, which means the amount of paint purchased, X plus Y, has to be greater than 350. It would be really good if Neil purchased exactly 350 square metres of necessary paint, of purchased the necessary paint to paint exactly 350 square metres, but the simplex algorithm deals with inequalities and optimising inequalities. But this constraint has been omitted from the formula because the simplex algorithm deals with smaller than or equal to inequalities. So to use a larger than or equal to inequality, you need either the two-stage simplex algorithm or the big M method. And we're asked to use a simplex algorithm to solve a linear programming problem. I've not given an answer template, so you can't see the initial table. So we're going to try and construct one here. Our profit equation, our objective function, I'm going to rearrange, get P, subtract X, subtract Y equals 0. My first inequality, I'm going to write as 1.4x, I mean 1.45x, plus 0.95y, plus a slack variable S1 is equal to 400. My second equation I'm going to write as negative x plus y plus the slack variable S2 is equal to 0. So I can now write my initial table. I'm going to get basic variable x, y, S1 and S2. And I'm going to get a value. So my first equation, 1.45x plus 0.95y plus S1 is equal to 400. with basic variable s1. My second equation is negative x plus y plus s2 equals 0, with slack variable s2, basic variable s2. Finally, I'm getting my objective row, p subtract x subtract y is equal to 0. And instead of choosing our own pivots by selecting a theta value, which we could do, we're told to use this one. And this one would be what you would get if you used a theta value to select a pivot, if you used the y column. So let's use that value as our pivot column. I'm going to label my rows, row 1, row 2, and row 3. And now I'm going to perform the simplex algorithm. So I'm going to create a new table, basic variable, x, y, s1, s2, and value. And the second row, which has my pivot term in it, my pivot value, 1. Well, this second row, I don't need to do anything to it. My pivot value is already 1. I do need to change my pivot. My s2, my basic variable, is now going to become y. I'm going to get y, negative 1, 1, 0, 1, and 0. And my row operation is that row 2 is equal to row 2. My new row 2 is equal to my old row 2. Now for the other variables. For my objective row, I'm going to say that row 3, or my new row 3, is equal to my old row 3, which had a negative 1 in the pivot column. I'm going to add 1 to it, so I'm going to add row 2. I'm going to get p, I'm going to get negative 2, 0, 0, 1, and 0. And then I'm going to get my first row with basic variable s1. I'm going to take my row 1, and to row 1, I'm going to subtract 0.95 lots of row 2. And when I do that, I'm going to get 2.4, 0, 1, negative 0.95, and 0. I've not yet finished the simplex algorithm because there's still a negative in my objective row. So I now need to do the simplex algorithm again. I'm going to use x as my pivot column. I'm going to calculate theta values, and I've just realised I made a mistake. The value here is 400. So I'm going to create theta values. I'm going to get a negative here. We don't do it for the objective row. So the only one left is this one. It's positive. I don't really care what the value is because it's the only positive one. So this is going to become my pivot row now. So now I'm going to write my new table, basic variable, x, y, s1, s2, and value. And I'm going to write down my row operations. So my first row is now going to have basic variable x, and I want a 1 as the pivot term now. So I'm going to take my old row 1, and I'm going to divide it by 2.4. So I'm going to take my old row 1 and divide it by 2.4. If I do that, I'm going to get 1, I'm going to get 0, I'm going to get 5 twelfths, and I'm going to get negative 19 over 48 if I use fractions. And for my value, I'm going to get 166 and 2/3. Now on to row 2. And on row 2, I need to take my old row 2, which had negative 1 in the pivot column, and I need to add my new pivot row. So I'm going to add row 1 to it. I'm going to get 0, 1, 5 twelfths, 29 48ths, and 166 and 2/3. And finally, my objective row. My objective row, I need to add 2 lots of my pivot row to. So row 3, my new row 3, is equal to my old row 3 plus 2 lots of my pivot row. I'm going to get 0, 0, 5, 6, 5 24ths, and 333 and a third. And I could write these values as improper fractions. If I tried doing that, instead of 166 and 2/3, this would instead be 500 over 3. This would also be 500 over 3. And this would be 1000 over 3. Okay, so we've now completed a simplex algorithm. Where would the marks have come from? I've got to add the independent accuracy mark up there. Well, the 7 marks come from creating the objective row in your initial table and then having the entire table correct. Then you get a mark for using the first pivot correctly, so using 1 correctly and creating your second table as a second accuracy mark. Then another method mark for using the second pivot, identifying the second pivot correctly, and an accuracy mark for doing the correct table. And then we have forgotten to write out the final solution. The final solution is x is equal to 500 over 3, and y is equal to 500 over 3. So 166.67 square meters using expensive paint and 166.67 square meters using the less expensive paint. But this only gives us 333.33 square meters of coverage. And writing that information down would have been a final independent accuracy mark. So, the solution shows that Neil requires more paint and he negotiates an increase in his budget to £450. Find the solution to the linear programming problem given by changing 1.45x plus 0.95y is less than or equal to 400 to it being less than or equal to 450. If we increase 400 to be 450, we'd be dividing 450 by 2.4 instead of 400 by 2.4. So our values would become 450 divided by 2.4 instead of 500 over 3. And the values for x and y are the same. So the new solution for part 4, if we write it down, the new solution to part 4 would be 450 over 2.4 is x and y. So we're going to get that x is equal to 187.5 square meters, y is equal to 187.5 square meters. So the total coverage is equal to 375 square meters, which is now enough. Part 5, explain why the revised solution is not optimal for Neil. And this solution isn't optimal for Neil because, well, it's not giving him the maximum amount of expensive paint, given that he only requires 350 square meters of paint. Neil could instead buy some more expensive paint to reduce the coverage, but have an easier job applying this paint. So we're going to help Neil solve this. Neil needs to change the objective of a linear programming problem and add another constraint to it. And we're going to try and do just that. So let's write down the new problem. So part 5, Neil wants to maximise the amount of expensive paint he uses. So we're maximising P is equal to X. And then we're going to write our constraints. We're subject to 1.45x plus 0.95y is less than or equal to 450. We know that y subtract x is less than 0. X plus y, the total amount of paint used, is greater than or equal to 350. Hopefully it's going to be exactly 350 bar. And we know that x and y have to be greater than or equal to 0. So let's try writing this as a problem. So we're maximising p equals x, so we're going to get p subtract x is equal to 0. And to get 1.45x plus 0.95y plus s1 equals 450. We're going to get negative x plus y plus s2 equals 0. And then we've got to treat this constraint differently. We've got to subtract a surplus variable, S3, and add an artificial variable, A1. And that's equal to 350. So we want to maximise P equals X, but we actually have another constraint. We want to minimise I, or you could call it any other letter. We want to minimise I is equal to A1. So we want to maximise a function A equal to negative I. So if you minimise a number, then the negative of it has been maximised. And that's equal to negative A1. So we could rewrite this constraint as A, capital A, plus A1 is equal to 0. But we have a bit of a problem. We don't really want an artificial variable in our objective. So we're going to rearrange the equation above that has the artificial variable in. So we're going to get A plus 350 subtract x subtract y plus s3 is equal to 0. And we want any constants by themselves on the other side. So we're going to get A subtract x subtract y plus s3 is equal to negative 350. Now that I've said that, I'm looking at the mark scheme and I see that I appear to have not got the correct answer. So let's double check. So we want to minimise I is equal to A1. We want to minimise our artificial variable. That would result in maximising the negative of our artificial variable. And A1, and we can rearrange this and get capital A plus A1 is equal to 0. And we can replace A1 with 350 subtract x subtract y plus s3. Yes, so my apologies, I'm looking at the mark scheme and it's an old style mark scheme and they used the objective row differently for this. So we are correct here, fortunately. So we've now got all of our necessary equations, so we can write down our basic variables. We can write down variables x, y, s1, s2, s3, a1, and our value. And we've got 1.45x plus 0.95y plus s1 is equal to 450. With basic variable s1, we've got negative x plus y plus s2 is equal to 0. And we've got x plus y subtract s3 plus a1 is equal to 350. We've got basic variables s2 and a1 here. We can now add on our objectives. We're going to get p subtract x is equal to 0. And we're going to get a subtract x subtract y plus s3 is equal to negative 350. And the rest are going to be zeros. And this is our two-stage simplex algorithm fully set up. We are told that we do not need to solve it. But we do need to give a brief description on how to solve. So we want to maximize A. If A1 is equal to 0, proceed to stage 2. And maximize P. Excellent. And if we maximize it, we need to maximize A to equal 0. So if A is equal to 0, then negative I equals 0. So I will also equal 0. And this setup is worth 7 marks. So it's 2 marks for some of the equations. You're going to get 2 marks for this setup here. Well, 1 mark for this section here. Another mark for your maximizing A. You're going to get 4 independent accuracy marks for this table. 1 for handling surplus variables correctly. 1 for handling an artificial variable correctly. 1 for a new objective. And 1 for a new constraint. And last but not least, the brief description on how to solve is a mark. So thank you for watching, and until next time, goodbye.